Hi, so for today we're going to talk about the application of first order differential equation, and more specifically we're going to talk about laws of growth and decay. This is basically a continuation of our study all about the application of first order differential equation. So the laws of growth and decay states that the rate at which the substances changes is proportional to the quantity of substance present at any time t. Okay? So to put it mathematically, we have an equation dx over dt. Change of substance x with respect to time is proportionate to the quantity of substance present at any time. So we have this rate equation, okay? And if we are going to solve the general equation of this differential equation, we shall be arriving, or the general solution, we shall be arriving at this equation, where x is equal to c multiplied by e raised to kt, where x is the quantity of substance present at any time. If we are talking about decay, most probably if we are going to talk about population, okay, or growth, X could indicate the population. So, T is stands for time and K is the proportionality constant. Okay? So, let's try to solve some problems involving the laws of growth and decay. So, for the first problem, we have radium decomposes in air at the rate proportional to the present amount. If initially there are 20 grams, and after 10 years, 0.6% of the original amount decomposed. Letter A, set a model that will predict the amount of radium at any time, T. So, we are asked to have an equation that will predict the amount of radium at any given time, T. So, in order for us to do that, for letter A, okay, this is the very first thing you're going to do with the DE. Always set up the equation just like what we are doing in Newton's law of cooling. So, we have the rate equation dx over dt is equal to kx. Okay? If we perform separation of variable, dx over x would now be equal to k dt. Okay? And if we integrate both sides of the equation, we'll be having this, okay? Dx over x is ln of x is equal to kt plus arbitrary constant c, or the constant of integration c. So if we raise these two equations, both sides, if we exponentialize this, okay, so exponentiate, so we have e raised to ln x would simply be x, and we have e raised to kt plus c. But by laws of exponent, we have x is equals to e raised to kt multiplied by e raised to c. But e raised to c is simply equal to c. So we have now our general solution a while ago that we have. Okay? I've derived it for you to understand how did we arrive at that general solution. That is not the answer for letter A. Okay? As you can see here, x is the amount of substance at any time t. So, if we plug in any values of t in this equation, we could definitely get the x, given that we know the value of c and we know the value of k. So, just as like in our Newton's law of cooling, we need first to determine the values of c and the values of k and arrive at a certain equation that would give us the amount of radium x at any time t. So, let's try to find the values of C and K. Okay? So, at time is equals to 0, okay, initially, okay, our value of X is 20 grams. That's what the problem says. Okay, so we have, if initially there are 20 grams, that is time is equals to 0, X is 20 grams. So if we're going to substitute this condition on our equation, we have 20 is equal to C e raised to K times 0. K times 0 is 0. E raised to 0 would become 1. So definitely our answer for C is equals to 20. Okay? After we determine the value of C, it's now time to determine what is the value of K. Okay? So, if we determine the value of K, so we have the second condition, it tells us, okay, after 10 years, 0.6% of the original amount decomposed. So, it means at time is equals to 10 years, okay? The value of x now would be reduced by 0.6% of the original amount. How do we compute that? The original amount is 20 minus, okay, 20 multiplied by 0.6% is a percent. If we want to make it as a decimal so that we can multiply it by 20, that should be 0.006. We will be dividing 0.6 by 100. And if we're going to get the amount of radium, okay, after 10 years, that should be 19.88. Okay? 19.88 grams. So this would be the amount of radium after 10 years. Okay? So, back to our equation, we simply substitute. Our equation is C e raised to KT, but we know the value of C, and we are given for X, 19.88 is equal now to 20, which is the C a while ago, E raised to K multiplied by T, which is 10. Okay? So we have now 19.88 is equal to 20 E raised to 10K. Okay? By algebra, we need to find K. So 19.88, divide both sides by 20, we have E raised to 10K. And if I'm going to take the natural logarithm of both sides of our equation, we have ln of 19.88 over 20 is equal now to ln e raised to 10k. Okay? So this would cancel definitely. Ln of e would cancel. We are left with, on the right side of the equation, 10k is equals to ln 19.88 over 20. And to get k, simply, we have k is equal to 1 over 10 ln of 19.88 over 20. And now we have our answer for letter A, a model equation that would compute the amount of remaining radium at any time t. So, going back, so our answer would be X is equals to CEKT. Our value of C is 20. E multiplied by K. What is our K? That is 1 over 10 ln of 19.88 over 20 multiplied by T. So this is our answer for our first question, letter A. A model that would give the amount of substance at any time t. C, if we are going to substitute any values of t here, since we know the C and K, we can arrive always at a certain value X. So that is the answer for our letter A. But for letter B, let's try to solve. Okay? Letter B, what is the half-life of the radium? When we say, let me rephrase the question. When will the radium be half-life? Okay, when? Okay, the half-life of any amount is we are going to divide by 2 the initial amount. So if initially we have 20 grams, the half-life of 20 grams is 10 grams. Okay, we are asked what is the time it takes for 10 grams, okay, to decompose. So plugging it into our equation, this is our model equation. It is important always to get the model equation. Okay? This is our model equation. Plugging it in our model equation, we have 10 is equals to 20 E 1 over 10 ln of 19.88 over 20 multiplied by T. Okay? And we need to solve for T. But before we do that, if I'm going to divide both sides, okay, the question is when, okay? When will be the radium have a half-life, okay? That is the question. So, if I'm going to divide this both sides by 20, so we have 10 over 20 here, and we have, by properties, okay, this T is multiplied to the whole expression K. So, I can rewrite this as T over 10, okay, or 10 or T times 1 over 10 ln of 19.88 over 20. Okay? So 10 over 20 is 1 half. And by properties of natural logarithm, I can put this as the exponent of the ln. So we have e raised to ln 19.88 over 20 t over 10. So, we can cancel out e raised to ln. That's right. So, we are left with 1 half is equal to 19.88 over 20 t over raised to t over 10. And we need to solve for t. And if we're going to get the natural logarithm of the both sides of the equation, so we have ln of 1 half, ln of this, by properties of natural logarithm, I can put this exponent again on the before the ln. Okay? So we have t over 10, ln now of 19.88 over 20. Okay? And we can now solve for t. Okay? If we multiply this both sides by 10, we have 10 ln of 1 half is equal to t ln of 19.88 over 20. Okay? So we can solve now for letter t because that is the time it takes for the radium to have the half-life, which is 10 grams. So we have t 10 ln of 1 half over ln of 19.88 over 20. So if we're going to evaluate that with our calculator, let's try 10 ln of 0.5 or 1 half ln of divided by ln of 19.88 over 20. The time it takes is for it to have a 10 gram, okay, substance, that is 1,151.78. The unit of time is years. Okay, at least for this problem. Okay, at least for this problem. So that is our answer. When will it reach its half-life? Okay, when? Okay. Number 3, what is the amount remaining in 900 years? Okay, this is very pretty obvious. Okay, we have now our model equation a while ago, and our model equation is x. What would be the amount remaining after 900 years? Imagine. So we have our c is 20, e raised to, what is our k again? K is 1 over 10, okay? ln of 19.88 over 20 multiplied by t. Take note that t is not inside the ln. It is multiplied by t. Okay? So, in other words, if I'm going to do this, 20 e raised to t over 10, ln of 19.88 over 20. Okay? Plugging it, at time is equals to 900. Okay, so we have x is equals to 20 e, okay, raised to 900 because that's our time, 900 years over 10, ln of 19.88 over 20. And our answer should be, if we input this, let me just calculate it. So we have 900 over 10, ln of 19.88 over 20. Our answer should be what? 11.63. Now, what is this 11.63? That should be in terms of grams because initially the given is in terms of grams. So we expect that what we get is also in terms of grams. So that would be the amount remaining radium after 900 years. Okay, let's try another problem. So for this problem, again, it's a problem involving a decay of certain element. So again, radium decomposes in air at the rate proportional to the amount present. It is found out that in 25 years, 1.1 certain, okay, of a certain amount is decomposed. Determine approximately how long will it take, A, for 1 half of the original amount, okay, this is original amount, okay, original amount to decompose. Okay. There is a great difference between our problem a while ago and in this problem. As you can see here, okay, the amount of present, okay, is not initially given. Okay? So, it only says that after 25 years, 1.1% of a certain amount is decomposed. But, initially, the problem does not give us any initial X. Okay? So, if we are not given any initial x, it is safe always to assume, okay, let's say, assume x is equals to 100 grams, okay? Whether it be or population or substance, let's assume 100 grams, okay? So, but if it is given, you should use what is given, okay? But if it's not, it's convenient to use 100 because we are dealing with percentage, okay? Always. So, assume that x is 100 grams at time is equals to 0. That's the initial amount of the radium. You can also use 50, you can also use 20 grams, but 100 grams is much easier because we are dealing with percentage. Okay? So, assume that we have 100 grams at times equals to 0. Our model equation or our equation, general equation is this. Okay? I've derived this a while ago. So, we need to find C again. Okay? First, we need always to come up with a model equation, even if it is not asked in the problem, so that you would be able to solve for what is being asked in the problem. So we need to find C and we need to find K. So initially, we have 100 is equal to CE multiplied by E raised to K times 0. So this is K times 0. This is equal to 1. So C is our 100. Okay? So, another condition to solve for K, it says it is found out that in 25 years, at time is equals to 25 years, okay, the amount is decomposed by 1.1%. Okay? The amount is decomposed by 1.1%. So, if 1.1%, we have a 100 grams minus 1.1 grams because the 1.1% of 100 is 1.1. So definitely, if we do that, 100 minus 1.1, that is 98.9 grams. So that's why I chose 100 as I assume 100 grams because it is easier to compute. Okay? Just like what we did here. So again, after 25 years, the original substance decreased by 1.1%. And the 1.1% of 100 grams is 1.1 grams. So that we subtract 1.1 from 100. So we have 98.9 grams. So again, our condition, we have 98.9. That is the value now of our x after 25 years. Is now equal to value of C, which is 100. E raised to K multiplied by 25 because that is 25 years. By algebra, we have 98.9 over 100 multiplied by E raised to 25K. And if we get the ln of both sides, we know what will happen. ln of 98.9 over 100 is equal now to ln E 25K. Raised to 25K, we have now ln of E cancelled. So we are left with 25K here. And we have ln of 98.9 over 100 here. In order for us to get K, we have K is now equal to 1 over 25 ln of 98.9 over 100. Okay? So that should be our equation. So our model equation now will be x is equals to the amount of substance X at any time t should be X is equals to the value of C is 100 multiplied by E raised to 1 over 25 ln of 98.9 over 100 multiplied by T. Okay, this is our model equation. Okay, so and therefore if we get the model equation, if we know the value of C and K, we can therefore now answer what is being asked in the problem. So for how long will it take, this one, how long will it take for 1/2 of the original amount to decompose? So 1/2 of the amount. So it means at x is equals to 1/2 of 100 is 50, what is our time? Okay? So what will happen? We have 50 is equal to 100. E, okay, I can multiply this onto this. So we have T over 25 ln of 98.9 over 100. Okay? And if I'm going to divide both sides by 100, we have now 50 over 100 is equal to By loss of natural logarithm, we have ln. I can have this as my exponent. So we have e raised to ln 98.9 over 100. Okay, t over 25. And I can cancel out e raised to ln. 50 over 100 is 1 half. So we have 98.9 over 100 t raised to t over 25. So if I'm going to get the natural logarithm of both sides of the equation, okay, ln of 98.9 over 100 t raised to 25, by properties of ln, I can put this exponent before the ln. So we have ln raised to 1 half, so t over 25, ln of 98.9 over 100. Okay? And I can get t. So t would now be 25 ln of 1 half over ln of 98.9 over 100. And the value of t should always be positive because there is no such thing as negative time. Okay? So, let me just calculate this. Better if you have your calculator with you. So, the time it takes for it to achieve its half-life or half of the original amount, which we assume to be 100, so that should be after 1566.65 again years, because the unit that we're going to talk about here or talking about here initially given is in terms of year. So that is our answer for letter A. Approximately how long will it take? It would take 1,566.65 years. Okay? So for letter B, determine approximately how long will it take. Okay? 20% of the amount to decompose. So 20% of the amount to decompose. If I have 100 grams, the 20% of 100 grams is 20 grams. So we are talking about 80 grams here because it decomposed 20%. So our x should be 80 grams. Okay? So, what is the time? Okay? For it to reach 80 grams. So, given in our model equation, again, our model equation would now be x, again, is 100, e raised to 1 over 25, ln of 98.9 over 100 multiplied by t. We need to solve for, again, for t. So we have 80 is equals to 100 because x is our 80. Okay? Again, e raised to ln of 98.9 over 100 t over 25. That's what we did a while ago. This would cancel. And dividing both sides by 100, I have 80 over 100. Okay, is equal now to 98.9 over 100 t raised to t over 25. If I'm going to simplify this, okay, or get the ln of both sides, what is this? 4/5, okay? The lowest term of this is 4/5. So we have ln also of 98.9 over 100 raised to t over 25. So by properties of ln, I can rewrite the right side of the equation as t over 25 ln of 98.9 over 100. So if I'm going to furthermore solve for t, okay, because that is what is being asked, what is the time, okay, for the radium to have 80 grams, okay, remaining. So we have 25 ln of 4 over 5 over ln of 98.9 over 100. Okay? Let me solve this 25 ln of 4 over 5 divided by ln of 98.9 over 100. So we have an answer of 504.35 years. Okay? This should be our answer. After 504, approximately 504.35 years, the value of the radium would now be 80 grams. Okay? And lastly, let us go for letter C. What is being asked for letter C? What percent of the amount will decompose in 50 years? So what percent of the amount? will decompose. Okay? He is not asking what will be the amount after 50 years, but rather, what is the percentage, okay, that is decomposed after 50 years. So our model equation is this. So I can get the amount of decomposed after 50 years, but that is not our answer. So we have 100 e raised to 1 over 25 ln of 98.9 over 100. What is our time? Our time after 50 years, okay? So, if we evaluate this, okay? So, you can also rewrite this as 100 e raised to 50 over 25, okay? ln of 98.9 over 100, okay? So, if we get that, that is the amount remaining. That is not the answer. The problem is asking for us for the percentage amount decomposed, okay? So, we have 97.8, if I'm not mistaken. So, 97.8 grams remaining after 50 years. So, that is not the answer. But because we are asked what percent of the amount will decompose in 50 years, what percent of the amount will decompose, this is the amount after 50 years. To find the percentage, simply, our initial is 100 grams minus 97.8 grams. Okay? So, that is the percentage decomposed after 50 years. Okay? So, that is, let's say, this is 0.81. Let's have it two decimal places. Let me just recheck this again. Okay? So, we have 97.81. So, 100 minus 97.81 is 2.19. Okay, so percentage is 2.19%. Why did I say so? So, the amount remaining after 50 years is 97.81. Okay? So, if I'm going to get the percentage of this, okay, I'm going to subtract the original minus the amount remaining. And that is since we assume that we have 100 grams, okay, so the percentage would now be the initial minus after 50 years, which is 2.19%. That is the amount decomposed, percentage amount of decomposed after 50 years. Okay? So another way to look at this is if we minus this, 100 grams minus 97.81, we'll be having 2.19 grams. And if we are going to get the percentage of this based from the original amount of 100 grams, that should be 2.19 grams over 100 grams multiplied by 100. As you can see, the 100 would cancel. This is 100 because percentage. So we are left with 2.19%, which is still our answer here. Okay? So let's go now. Let's go now to our last problem. So our last problem, the population of the town grows at the rate proportional to the population present at any time t. The initial population of 500, okay, that is our x, increases by 15% in 10 years. What will be the population in 30 years? So this is a problem all about the loss of growth. Okay? Population, as time goes by, the population is growing. Okay? So, we have an initial value of 500 at time is equal to 0. Plugging it into our general equation of our DE, we have 500 is equal now to C e raised to k times 0. Okay? Of which this is only equal to 1. So, therefore, C is equals to 500. Okay? And down to our second condition to find K, it says, at time is equals to 10 years, okay, the population of that certain town increases by 15%. So, our value for X should be 500 plus 0.15 times 500, okay? So, because it increases. So, after 10 years, it should increase by 15%. So, 500 plus 0.15 times 500, that should be 575 populations. Okay? So plugging it in our equation, again, this. So we have 575 is equal now to 500 because that's the value of C. E raised to K times 10. Okay? So we have 575 over 500 is equal to E raised to 10K. If we ln or have the natural logarithm of both sides, so we have ln of 575 over 500 is now equal to ln E raised to 10K, of which this should cancel. So we know what would be the value of K. The value of K should be, okay, 1 over 10, okay, ln of 575 over 500. Okay, so we now have the model for our equation. And our model for our equation is at the population at time any t or at any time t is should now be 500 e raised to k 1 over 10 ln of 575 over 500 multiplied by t. And this can be also rewritten as x is equals to 500 e raised to t over 10 because this is multiplied again, ln of 575 over 500. So the question is, what will be the population in the next 30 years? So at time is equals to 30 years, what would be the x? So simply, we're going to substitute 30 years in our equation, in our model equation, 500 e raised to 30 over 10 ln of 575 over 500. Using our calculator again, we can get the value of the population after 30 years. And the value of our population, okay, after 30 years is 760. Okay? As you can see, 760.44. That is what the calculator will give you. But there's no such thing as 760.44 population. So either we'll round it up or round it down. So approximately 760 people. Okay? So that's all for today. Thank you so much for listening. This is Engineer Abat. See you again for another video of the application of DE on the next video. So thank you so much for listening and God bless, and I hope you learned something today.